This is the experiment for first year lab, first semester. So for this experiment, we're checking the verification of theorems of perpendicular and circle axis. Well, the verification of this theorem basically surrounds around the principle of moment of inertia, where we have got the two factors here. Iz is equal to X plus L. Iz is equal to I naught plus V. So for finding this moment of inertia, we first need to find the timings of oscillations, the amount of resistance that occurs because of the delay in the oscillations. So when we find the time that each oscillation takes, we need a ground basis of finding out the moment of inertia.
So first we'll get an overview of how the page looks like and how we continue with the experiments. So as you can see, the apparatus is a rectangular wooden block, knife edge, stopwatch, meter scale, and ordinary balance. Now, before jumping into the apparatus, let's talk about the principle. You can see that Ix is equal to moment of inertia about x-axis, that is parallel to length. Iy is about y-axis, and Iz is equal to z-axis. Now, I'm passing to the intersection of x and y-axis. Now, according to the theory of perpendicular axis, this is the formulation that's been given. And according to and the moment of inertia of the lamina about axis passing through its center of gravity and perpendicular to the plane is given like this. Now, M is the mass of the block, L and B, and we have got the, according to the theorem of parallel axis, we have got the formulation as this. Now, if the block oscillates about x-axis parallel to its length, we will keep on switching each of the axes, just Iy with Ly, Iz with Lz, and continue with the experiment. Now, let's look into the other page. We will see that we have got a similar drawing of the wooden board that we'll be using. We have taken that Lx and Ly. While we have brought this into intersections, we are just looking into a smaller part of the entire wooden board because moment of inertia is going to be similar anyway. So we have this 6 specifications to mention that we'll find from the board itself when we observe it. Okay, now one of the other derivatives first apparatus that we discussed about is the rectangular wooden block. Now this rectangular wooden block is much uniform wooden block that we have in our space, very small. So you can see the specifications of the LX, LY, and LZ, right? So the LX, LY, and LZ will be measured according to the oscillations that's given to us. Now these oscillations will vary, but we keep them in their positions. So we have got here there are two stands with flat stands. And we can see the specifications of LX given like this. This is the x-axis that we have taken. So the x-axis will vary it with the help of and we would be giving it a specific amplitude, and the reason is continue to oscillate. So once it oscillates, it basically goes one, goes here, then it comes back, that's one oscillation. So and it's similar for the y-axis, you just have to extend it along the here, and then oscillate along the y-axis. So we have to be very careful with the specification of oscillation. Oscillation is when an entire object comes back to its new position after covering an entire distance. So we have to keep on counting it very carefully according to the text of words. And the oscillations for L we are going to calculate is one standard. So we have kept a balance in case there is a good balance with the movement of the different distance. And we count the LZ oscillations with the help of this one leg a little bit side, and we will be oscillating it in this function. Now the LZ oscillations are a bit ununiform because of the size of the hole. So we have to be very careful while counting it, and there can be slight errors. But rather of all major would be. So now we have come to the main experiment, that is the main table that's given to us here. So you can see that there are 1, 2, 3, 4, 5, 6. There are 6 main columns that we need to talk about. First is the time taken for 20 oscillations along x-axis. So according to the procedure that we have seen in the past, we have seen that we have to oscillate it 20 times past and forth. How much it takes for the 20 oscillations to occur. So now we are going to shift our focus that we also have a stop clock. So the stop clock is basically this is the start of stop clock. You can reset it with this. And then when the 20 oscillations, as soon as you leave that board and one oscillation takes place, we start it and we're going to count how much it takes for 20 oscillations to take place, that particular position. So the same goes for y-axis and z-axis with the same concept. And this is the mean time that's taking, that the period for one of the oscillations to take place. That's the time period given to us. So it's very simple. We keep on measuring it. We expect a much more like consistent value, because basically for z-axis you can see that there is some values like a bit error, because the z-axis wobbles a lot more compared to x and y-axis, which are much more stable. So you don't really need to worry about this, because as long as the values fall between somewhere in this range, it is considered a good enough value to continue with. So we have reached almost the end of the experiment. While we get our mean values for each oscillations, we put them into this formulation for sure. And with this ix, iy, iz, we'll be verifying the experimental values with the values that we have gotten from ix and iy. So from the experimental value, we can see that the mean dz has to be 0.94 seconds. We put it in here. And from here, we get a value of, in here, it's 0.026 kg meter square. So we will be using the parallel axis theorem and the perpendicular axis theorem, the same formulation. You have seen the calculation here. So we are using the I naught plus MLZ squared, and IZ is equal to IX plus IY. To continue with the rest of the experiment, and then we will verify how close the values are. You can see the values are pretty nice here, 0.028, and the IZ is coming to 0.026. So the conclusion is perpendicular and parallel axis theorems have been verified, and this verification matches us with the aim of the experiment, meaning that the formulas are experimentally and theoretically correct.